since I sat in this room myself as a student. Not very much. Not very much. New chairs. This is great. This is great. I'm very pleased to be here.
Okay, so let's get started. So it's a pleasure to have Brian Pyper here today. So he is originally from Salt Lake City, so welcome back.
Thank you.
And so Brian is currently a distinguished professor of physics at BYU, Idaho, and also the director of the physics education there. And Brian obtained his bachelor's degree at BYU, and his master's degree here in physics, and PhD at Utah State University. So Brian,
going north all the time.
My whole life.
Okay, so Brian founded this BYU Idaho student research conference in 2006, and served as a director for 6 years. And this turned out to be a very successful conference. And Brian also served twice as the president of the Idaho Utah section of the American Association of Physics Teachers. Brian did a lot of research in physics education, and today he's going to tell us what he found.
Thank you. Thank you. I'm flattered and pleased to be back here. I think I've been back here a couple of times over the years for AAPT meetings here at the University of Utah, but otherwise, this is my first time back in this room in 20 years, 19 years. But it was here in this room that the course of my life was changed. And it was in one of these meetings like this, you graduate students, I'll tell you it was worth it to keep coming to these meetings, even though I fully understand exactly how that feels. I graduated from BYU in 1991, and that spring, it's just a brief history. This will just take a second. Just be patient. That spring, Stephen Jones and a researcher from Arizona named Rafelsky were going to come to BYU and give a colloquium like this about their research in muon-catalyzed low-energy nuclear reactions. And two chemists that were here at the University of Utah implored him to postpone this colloquium for a month because they were jointly working on different aspects of the same problem. And so he did, postponed it from about February into April. And in the intervening time, those two chemists announced that they had achieved lattice-catalyzed fusion reactions. And they had a big press conference, and the university and the state legislature gave them several $1 million to found a center over here in Research Park. And by the time I got here in the fall of 1991, the fever of cold fusion was fully enacted. So I started working with Haven Bergeson, who many of you will remember, on trying to verify some aspects of what was going on in the palladium lattice. And that ended up being my master's project, and it may have turned into a PhD dissertation, except for two things. The first one was that I failed the common exam. And the second one was that the university, as I was finishing my thesis, sold off all of its cold fusion patents because it had turned out that the two chemistry researchers had fabricated their data. So that was all in the thick of that time. So in the intervening years, I taught high school here in Salt Lake for several years, and then ended up at Ricks College, which changed to BYU Idaho. And since I was ABD at the time, they sent me back to school, and I did my research at Utah State, and have been in Rexburg pretty much ever since. Have been very happy there, and have come up with some pretty important things, I think, about how people learn, particularly how people learn math and physics. So I hope that for those of you who are teaching or who will teach or who are learning or will learn, that what we're going to talk about here today will have an impact for you. This is sort of what I want to try to do. I will just give you a short history of physics education research and sort of the major players in who have been involved in discovering different aspects of what we're going to talk about here. Some of the key findings in different areas of what we care about in physics, and then I'll talk a little bit about the research that I've done with respect to reasoning ability and how that impacts how we learn. All right. From the time that the APS, the American Physical Society, was founded until about 1930, there was an aspect of the American Physical Society, which was sort of the premier organization for physicists in America, that cared about education, but didn't really give much more than this is a new cool way to teach this or that thing, or a new demo that I build, or something like that. In the early 1930s, these three men, Homer Dodge, Paul Klopsteg, and Floyd Richtmeier, sort of created their own society out of that sort of education community in the American Physical Society called the American Association of Physics Teachers. And they still sort of revere these three men in the AAPT as the founders of that society. And then when the Manhattan Project came around in the 1940s, the emphasis on science and education changed a lot of how we thought about what had to happen with respect to physics and society, so that the way that we educated pre-service teachers especially, but also the graduate students in physics, changed a little bit at that time. Then the Sputnik was the next big thing, and particularly in America, the race to keep up, or so we felt, with the other nations that were getting things up into space really put a lot of pressure on the American education system to produce scientists. Then, and you know, this is going to be a recurring theme here about how curriculum impacts education, because the first edition, which you see here, of the Halliday and Resnick physics book was published in 1960. And that turns out to be a big deal, because those of you who, during that time, may have studied out of any of the other competing physics textbooks at that time, like Sears and Zemansky, for example, Halliday and Resnick was a whole new baby. The way that they approached trying to teach people physics was totally different. And it was a subtle change, and we'll talk about that subtle change. These two men, Arnold Ahrens on the left and Bob Karplus on the right, were both, I think actually Ahrens was a solid state guy and Karplus was a high energy guy. Both of them sort of migrated from their standard places in physics to physics education by virtue of their kids. They had kids in the education system and felt like that what was happening to them was not preparing them well for what they saw what the future was going to look like for science. And so they got involved. Karplus is the one who developed what we now call the learning cycle. And we'll talk about that more in a minute. But that was a big deal. And in educational circles, the educational psychologists still talk about the learning cycle as though it was one of theirs that made it up. But no, it was one of us. Okay? Ahrens wrote this book. There's an earlier version that's called A Guide to Introductory Physics Teaching that was published in 1991. It's a kind of a tan book. This one was published in 95, I think, 97. And still, if for high school physics teachers or for somebody that wants to teach physics, this is the Bible for physics teaching. Okay? And I make my pre-service high school teachers all buy this book, in spite of the fact that it's like $60 now because it's starting to go out of print. Crazy. But these guys were major players in that change, because the shift was, and it was represented by what happened with Halliday and Resnick, was from how do we teach physics to how people learn physics. Okay, if you're thinking about what's happening to your students as you're teaching, instead of how am I going to do this, You might think that's not a big thing, but it's a subtle shift, but crucially important. Okay, the difference between I am the one and you are the one. Okay, and that turns out to be really important. So in the course of the intervening maybe 20 years after that, so and we'll come back to this, but in the middle part of the 1970s, Ahrens and Karplus got together and did some research about what was happening with how people learn physics and what was happening in American physics. Lillian McDermott worked with Arnold Ahrens at the University of Washington, Fred Reif at Maryland, and Joe Reddish. Priscilla Laws is at Dickinson, Alan Van Heuvelin at Ohio State, Zine Zolman at Kansas State, Jose Mestre, who is now at Illinois, but at the time was at UMass Amherst, and Sheila Tobias, who is recently retired from Arizona State. We're all players in this and have pioneered different aspects of what happens in physics education. Now, I want to point out particularly, Sheila Tobias came here to the University of Utah in the spring of 1993, about. Do you remember? It was in that time period. And she gave a talk here in this room about using scientific research methods to study about how people learn. She was a math education researcher and was focused at the time on sort of math phobia kinds of things. And at the time, I was just finishing my research with Haven Bergeson on lattice-catalyzed fusion reactions. And I was very much enjoying my teaching the tutorial and discussion sections that were assigned to me as part of my graduate work. And her talk changed the course of my career. And as a result, I finished my master's here and transferred over to educational studies and discovered a dysfunctional collection of political goofballs. So after I had finished all my coursework over there, I took a leave of absence, and it was about that same time that I got the job at Rick's. So this turned out to be important for me. But these are some of the early players in PER. Now, I want us to move forward now to 1991, because in 1991, in the American Physics Teacher, what now is the Physics Teacher magazine, David Hestenes was the principal researcher in this group, and there were about 9 people that together wrote a test that was published in the March issue of the Physics Teacher magazine that was called the Forced Concept Inventory, and they had a whole host of data and people that they tried it out on, from high school to college students, and having a nationally recognized, vetted, tested inventory of basic physics concepts changed everything. The main thing that happened as a result of that is that people like Eric Mazur, who was and still is at the Harvard-Smithsonian Center for Astrophysics, is a physics professor there, a distinguished, I think he has a named chair now. But, pardon?
He will be here in the fall.
He's coming here in the fall. There you go.
Originally, this semester, but there's an accident.
Okay, very good. There's a good. You can ask him some good questions then. He looked at the forced concept inventory, as many other people did, and said, this very basic, simple conceptual questions with no equations and no difficulty, stuff like that, my students are going to eat this for lunch. My Harvard students are going to have no problem with this. And he gave it to them, and only 10% of his students got better than 60% on the forced concept inventory. He was stunned. And as a result, completely changed the way he taught. Richard Hake, about 4 years later, collected the several thousands of students' data that had taken the forced concept inventory to that point, and published also, no, this one was in AJP, published in about 1995, a paper entitled a 6,000 student meta-study of results from the forced concept inventory. And what he was able to show was, and this still is a little nebulous for folks, but he was able to show that classrooms that were more interactive had better results on the forced concept inventory than straight traditional lecture courses. So that sort of began what now, with the flipped classroom stuff, it began the migration away from more traditional lectures, at least at the undergraduate level, to a more interactive kind of classroom where now we have clicker questions and tutorials and things like that. And we'll talk more about how all that has impacted things. But Richard Hake is the paper that wrote that, is the guy that wrote that paper. And the metric that he used to gauge changes in conceptual understanding, they still call the Hake gain because of that. And it ends up to be a normalized gain where you take their score on the forced test of the forced concept inventory minus their score on the pretest, divided by 100 minus the score on the pretest. So it's a measure of their gain relative to how much there was to get. Okay, and they still call that the Hake gain. He now, Richard, on the listserv, the email listserv of the people that do physics education research, he is the self-proclaimed arbiter of the curmudgeonly society of, I don't remember all of the acronym, but he models it well. So this is now on Compadre, which is sort of the physics education research website. This is the places where you can get a graduate degree in physics education research. Okay, some of these are larger than others, and you know, you can see this one down here is Genaro Zavala's group at Tecnologio Monterrey, Maryland, and Illinois, and K-State, and Washington, UW. Anyway, oh, and there's a big one at UC Boulder now, where Carl Wyman is there.
What sorts of departments do those programs tend to reside in?
They are all in physics departments, which is as it should be. And I'll make an argument for why that's so, but, and this has been kind of a long road, because many physics departments will say, oh, that education stuff belongs over there in that other building. And the education people say, physics, what's that? So my argument is that this does belong in the disciplines. It's a discipline-based educational research system because we have the content. And I will argue, and maybe this is idiosyncratic, but I will argue that it's easier for a physicist to figure out a little bit of statistics than it is for the educational researcher to figure out Brockett notation. Okay? All right. So, what's happening now in PER are all of these various lines of attacking the question of how do you teach and learn physics. Okay? Misconception research is a big deal, and we'll talk more about that. Looking at differences between experts and novices. That's kind of older stuff, but is still popular. This was back in the late 70s. This was a big deal about looking at the difference between expert and novice chess players, and try to say about what was the difference between how they thought. And they've done studies like this in physics as well. Developing new curriculum, the impact of technology in the classroom, looking at differences with ethnic backgrounds and gender effects on what is happening in the classroom. Techniques to teach problem solving. You know, I had a discussion with Red earlier about what it really is that's at the core of why we value studying physics. Okay, and if you think about that for a minute, most of us will say it's the way physicists solve problems. How we think about solving problems. Yeah, have you heard the spherical cow? Mm-hmm. You know that joke, the spherical cow joke?
Well, how many of them are there?
That's a good point. There's a book that Larry Krauss wrote. It's called The Fear of Physics. And he tells that joke at the beginning of the book. And the cover of the book actually has a picture of a cow that's sort of shaped like a sphere jumping over the moon. And his point in that book is that when a physicist asks about how do you solve this question, what they do is they assume a spherical cow. They take all the parts of the problem that are peripheral away, and they solve the core problem. What does this look like in the absence of air resistance? What does it look like in the absence of friction? What does it look like, to the second order? Whatever, however you want to describe that, and they solve that core problem. And then they say, all right, now what if we add back in gravity? What if we add back in friction? What if we add back in air resistance? And then you say, okay, well, some of this gets to, nonlinear coupled differential equations, and so. But that's how physicists think, and that's the value of studying problem solving. How do you teach somebody else how to think that way? Okay, so looking at it from cognition and from a neuroscience point of view, several researchers have done that. There's been a couple of studies lately looking at eye tracking software, where you put stuff up on the screen and ask them to solve a physics problem, and then look at where their eyes are pointing on the screen to see what they pay attention to. Okay, this is important. It's a big deal. Preparing teachers and how to prepare teachers to teach in these more innovative ways. Attitudes affect how you feel about what you're learning, and epistemology, what does it mean to know something? Those all affect how you approach what's happening in the classroom. And reasoning, some of the stuff that I've done. We have the Physics Teacher magazine, the American Journal of Physics, Physics Education, which is published by the Institute of Physics in England. And relatively new, we have a PhysRev Special Topics in Physics Education Research. That's a free online journal if you want to kind of go see what the cutting edge stuff is that's just being published. Then that's the place to go. Okay, so let's look at some of these individual pieces about the PER-friendly classroom. Okay, so what's really happening when you learn something? In your brain, there are neurons that are cells that are connected to each other. And that when you learn something, what a memory is collections of these neurons that fire together. Okay? That's what a memory is. So when you go to somebody and you say, what do you think about this? They say, we'll give you an example. Okay? Because people never stop learning. That's what humans do, is make sense out of what happens around them. We're always, constantly, all the time learning. Okay, so as a little kid, when you look up in the sky and you see that the moon appears to be different shapes, for example, the common, we call it a phenomenological primitive, the idea in your head about what causes the phases of the moon. Okay, if you were to ask 25 people out there on campus right now, 21 of them will tell you it's the shadow. It's the shadow of the Earth on the moon. Okay? No one ever told them that. No teacher ever told a kid, oh, the phases of the moon are caused by the shadow of the Earth on the moon. But nearly everybody thinks that. Okay? It's because you're trying to make sense out of stuff all the time. And in the absence of a more sophisticated way of thinking about things, that's what you go to, is what makes sense. And until somebody says, no, that's not what causes it. It's caused by the relative positions of the moon, earth, and sun at different times of the month. Right? They'll say, are you sure it's not the shadow? And you'll say, no, it's from the relative positions. And then when you ask them on the test, what's it caused by? They'll say, you told me to say relative positions. But still in the back of their mind, they harbor this idea that it's caused by the shadow. Okay? So, what you're trying to do is to take those neural connections that they have made from their childhood and just tell them, no, that's wrong. That's not how people change. That's not how you change your cognitive structures. What you have to do is say, all right, if that was true, then what does this mean? When you do this, then what will happen? Then they say, oh, it doesn't do that, does it? Now they're in what Piaget, and we'll talk more about Piaget, what he would say is they're in disequilibrium. Right? You've taken them from their stable position at the bottom of the potential well and put them someplace that's uncomfortable. Now they got to say, okay, I got to refigure this. Now you provide them with the opportunity to reason through something that is a more sophisticated way of thinking about that, and they come to a new place. But that's what learning is. It's these cognitive structures that don't change just because you told them the right answer. They've got to do that themselves, and it's hard. sometimes when it ends up like in history of physics sorts of things, when you got to change the idea that the Earth is at the center of the universe, when it's tied to other cultural and ecclesiastical sorts of things, it's really hard to change. Because if you got to change your idea about where you are in the universe, that's a little more scary. So when you are trying to get people to change their ideas about some of these deeply held misconceptions, it's not just a matter of learn this new way. You got to totally change how your brain is connected. So that's the whole thing about misconceptions. I'll give you another prime example. Most people in a
Is that actually true with the 21 people?
it absolutely is true.
Someone has studied this?
Yep. I recommend, if you would like to go online and look up A Private Universe. It's a 20-minute movie that was published by Harvard about 15 years ago, something like that. And they interviewed people in their graduation robes at Harvard and said, what causes the seasons?
Was it Jay Leno or?
No. No, it was Philip Sadler is the guy's name that did this research study. And they asked him the phases of the moon, they asked him the seasons, and for engineers, they asked him, if we give you a wire and a light bulb and a battery, can you light it up? And most of them couldn't. Yeah. Yeah, one of my favorite is that they have one of the philosophy professors or something like that, and they ask him what causes the phases of the moon, and his answer is just nonsense. It's gibberish. And he's making these motions that are unrelated to what he's saying, and it's really, so I recommend it.
So with shadow, really people think it's the shadow of the Earth on the moon?
Yes,
Okay.
they do. And it's scary, because nobody ever taught them that, but we still figure it out that way. All right. Metacognition is another important idea, which it means thinking about thinking. Right? So if after you've learned something, not just say, what was it that you learned, but say, what did you used to think? What do you think now? Why are they different? Right? Sometimes people will call them learning journals. You give somebody a chance to go through and process what it was that they did to get from where they were to where they are. That really helps their understanding. Okay, that's a big deal. Metacognition. As we were talking about cognition and neuroscience, when you are trying to reconnect neural networks in the brain, so you're trying to change misconceptions from an unsophisticated way of thinking to a more sophisticated way, the chemicals that are present in the brain when that happens are important. And the chemicals that are released by the amygdala, which is the fear center or the excitement center of the brain, take those connections that are made and cement them faster to get them from what we might call short-term memory into long-term memory so that they stay there longer. They're easier to access in other settings. So if you're trying to take something you learned in a math class and transfer it to your physics class or vice versa, making connections like that across discipline boundaries, that is harder to do unless these connections are robust. And making them more robust occurs when these chemicals are present. Okay, and that can happen in, primarily two ways. If you're scared or if you're excited. Okay, so if you have a professor who's enthusiastic and is able to show you why what you're learning is important and get you excited about it, then that's better learning. It's not just that you enjoy it more, but those chemicals get present when the neural networks are established, and so they're more robust. You can do the same thing with, shock therapy. Right? If they're afraid that they're going to get shocked if they give the wrong answer, then learning occurs very quickly. Okay, so that's real science. It's not like that we're just making that up.
So does that mean you can just have loud noises go off at random? Lectures?
Yeah. There's an ethical part of all of that. Somewhat important too. One of the things that Aaron's pointed out is that in the process of this lecturing business, of moving away from lectures, and you'll have heard this in other settings as well, but his point was that you have 2 ears and 1 mouth. And as a teacher, you should use them in that same proportion. Okay? If you're not going to use them twice as much, you should listen at least as much as you talk. Okay? And I know that this is kind of a philosophical question, but if no learning is occurring, is teaching still occurring? Something to think about. All right, now one last point I want to make, and this is a real danger for physicists, okay? Because not everybody is like us. This is more than just we'll clink our glasses together and say, here's to us and those like us. This is more like in about 1974, Ahrens and Karplus took a brand new test, and I'll show you the ones because I use it extensively, and measured it, and it actually does this quite well. It purports to measure reasoning ability. Okay, so Piaget, let's see if I do this. No, not yet. Piaget was a Swiss-French researcher in the 1930s and 40s who came up with a system of talking about how people develop their cognitive abilities. Okay, and he had about 4 or 5 stages that he theorized occurred in people as a result of their maturing. Just because of their life experience as they aged, they would migrate between these cognitive stages. The first stage was what he called concrete reasoning, which is up until you're about 5 years old, where you can think about things that you are holding in your hand. Once they leave your hand, you don't think about them anymore. Okay? Then you have concrete operational reasoning, which is where if you did hold it in your hand, even if you're not holding it in your hand now, you can still think about it. This is highly simplified, but for a pre-operational reasoning, those were things that if someone else has held it in their hand, you can think about it. Okay? Formal operational reasoning was if no one has ever held it in their hand, nor could they, you could still think about it. Okay? So concepts like inertia, an idea like irony. Okay? Until you're formal operational, concepts like that are really hard to get your head around. You know, imagine trying to explain an idea like momentum to a little kid. Right? There's no place for them to put it. Okay? Ahrens and Karplus gave this test. It's called the Lawson Classroom Test of Scientific Reasoning. They gave this test to several thousand college freshmen. And what they discovered was only about 10% of those students were formal operational. Piaget said that should have happened by the time they're about 18 years old. So when we get into our introductory level of physics, and we start throwing things at them like electrons and electric fields and inertia and center of mass, you know, these are just ideas. They're not even really things that you can hold in your hands. If they're not formal operational, there's no place for them to put that. They don't have the reasoning. They don't have the cognitive structures yet to deal with that. Now, I don't know that that means that they're doomed to failure, because we have shown that you can change reasoning ability, and we're going to talk more about that. But with respect to physicists, I don't know if this is strictly true, but it probably is. Most of us are at a place where we will say, and this is sort of a way for physicists to show their pride, if you give me a textbook and a quiet, dark closet, just leave me alone for a minute, I can figure it out. Right? Isn't that true? That's how we live. Just leave me alone and let me talk about it maybe with somebody once in a while. Give me a book about it and I'll figure it out. Most people are not like that. That's not how they learn. So attributing our learning styles to other people is dangerous. Okay? The other part of that too is what you thought happened to you when you were learning is probably not really when you were learning. You know, if you want to say, I was learning in a lecture, oh, I was sitting listening to that other person talk. That's probably not really when the learning occurred. It was when you were at home fighting with it, you know, with your study group and with the textbook and maybe the solutions manual. That's when the learning occurred. Okay, so there both is that you didn't really learn it the way that maybe you remember you did, and that most people, it's not the way they learned. So it's worth our thinking about that when it's those people who are also going to decide whether or not we get funded. All right. The next thing I want to point out is the importance of active learning. Okay? Learning is a verb. It is something that you do. It is not something that happens to you, that someone does to you or for you or even near you. You have to do it. So that means that in the process of learning physics or literature or woodworking or whatever, you have to do it. So while we're sitting here talking about this stuff, if I really was going to be, you know, practicing what I'm preaching, we would be checking in with you periodically to see what you're thinking, to see if it's getting through, to let you be involved, to be actively engaged, minds-on, hands-on activities. Okay? One of the things I wanted to point out in here is that the senses, how that we are involved with the senses in the brain, turns out to be a big deal. Several years ago, I learned to play the bagpipes. I had to. It's my name. Piper.
Well, you could have played a smaller one.
I could have, but then it would be Irish. I don't want, we don't want to go there. No, but my bagpipe teacher was a good proper Scot named Dennis McMaster, and it turns out that there is a kind of solfege. Are you familiar with solfege? The syllables that you sing to help you learn do, re, mi, fa, sol, la, ti, do, the songs. There's a version of solfege for bagpipers. They call it cantoric. And associated with each of the fingerings on the bagpipe, there's a syllable. And then each of the different kinds of grace notes has a prefix that goes on one of those syllables. So if you finger the notes and sing the syllables in the pitches of the song, you memorize its song just like that, including all the grace notes and all of the repeats and everything. It happens very quickly. Okay, so the more that you can involve more senses in whatever it is that you're trying to learn, whatever it is you're trying to learn, the better it is. Okay, so if you can have a strong odor of ozone in the electricity demonstration, it'll fix that better. So consider that as you're trying to keep people involved in your lectures. Now that brings us to the question of demonstrations, and we've done a lot. I have done a lot of work with physics demonstrations. For the time that I was here, I spent 2 of those summers working with Zig Peacock, who is just my hero. I love Zig, but the time that I spent working with him really changed about how I think about teaching. The thing that often happens with demonstrations, with physics demonstrations, is that the kids think that they're just there to be entertained. And so they turn off whatever it was that you wanted them to learn about it. So what you have to do is to make them predict. Say, this is what I'm going to do, and this is the thing, and even though it looks like a black box, this is what's inside of it. Okay? This is what I'm going to do. What is going to happen? Make them predict. Make them get down off the fence. Okay? That pulls out whatever their preconception is and puts it up in the forefront of their head. Then, especially if you do something that surprises them, it's counterintuitive. Now they're in disequilibrium, and you can say, all right, why did it do that? That is what makes them learn. That's what makes the demonstrations worthwhile. If they think they're just there to be entertained, afterwards you'll say, you remember that demonstration? They'll say, yeah, I remember that demonstration. What was the point? They'll say, I don't know, I was just entertained. Okay? So, this is what we call the learning cycle, the 5 E's. This was Bob Karplus's contribution to all of this. Okay? First, you do sort of a pre-activity to engage them what's going on. Okay? Then you do some kind of exploration before they even know what it's called. Then you explain what happened. If you do the explain before you've done the explore, it doesn't stick. Okay? Then you evaluate and elaborate. And I added these little things here at the end. Explode, explain, excuse, and escape. As many times as over here one night in 103, I was in there giving one of my I think it was a test review. I was in there just, and I had all my students in there. There was 100 and something kids in there. And Zig was behind the door over in the demo area, and he threw a whole brick of firecrackers under the door. Lit it and pushed it under the door. Explode and escape. Yeah. He thought it was hilarious. Okay, so that's what we've talked about with demonstrations, and so that's something else for you to consider there. All right, we're almost to my stuff. Okay, action research is in the classroom while you're teaching stuff. Be paying attention to what's going on. Be thoughtful about what's going on in your classroom, and if you find something that's not working, in the spirit of empiricism, fix it. Don't do it the same way the next time if it didn't work. Okay, this is the core of action research. Okay, the methodologies that physics education research uses, these pre-post surveys and tests, case studies where you get somebody and you sit down with them and interview them about what's going on with their class, they are effective and they work and they give you good data that you can do research with, that you can talk about what's really going on, what learning is, and what has happened. Now, one of the things that people talk about all the time is that, smart people have thought a lot about some of this stuff, and there's no need for you to go out and reinvent stuff. Find something that works and pick it up and use it. Don't just reinvent the wheel, but reinvent the flat tire. Okay? If it didn't work for somebody else, try something new. So this book here, Randy Knight's book, 5 Easy Lessons, is cheap. You can get it on Amazon for like $6. It's an excellent book. Cliff Schwartz and Tom Minter have written this book, and this is available through AAPT. Joe Reddish, Teaching Physics with the Physics Suite. This one, when they first brought it out, they wanted to get it in the hands of so many people that I think at one of the AAPT meetings, they just handed it out. Gave it out to people for free from one of those textbook booths at the exhibitors hall. So these are out there and running around. And this one especially has an action research kit on a CD in the back of the book. So that's a good one. Okay? All right. So going back to reasoning, which is what my research of lately has focused on, we talked about the Lawson classroom test, and this graph, it was the kicker for me. Okay? Here's 60% on the Lawson test. That sort of is the boundary for formal operational reasoning. Okay, so this lower quadrant down here is people who are not formal operational. This is the percentage on the post-test of the FCI. It's not gain. This is just their post-test percentage. Okay, so what I want you to notice is that right here at about 60%, there's a step that you don't have access to, even 60% on the forced concept inventory unless you're formal operational. And this graph has repeated itself every single time that I have done this study in dozens of classrooms around the country. Okay, this is a big deal. This evidence, I think, shows that paying explicit attention to reasoning ability in your classroom is worth it. If what really matters to us is that they're understanding these concepts. Okay? And this is a similar sort of thing. This one's not quite the step function that this one was, but you can see nobody's above 60% on the FCI unless they're over 60% on the Lawson. Okay?
In the lower right-hand area, you've got a lot of points there. So the students are doing high on the well on the Lawson test.
Oh, over here? Yeah, so just because they're formal operational doesn't mean that they're going to get the concepts. But they're not going to get the concepts unless they are. Good question. Okay, so what about changing reasoning ability? What does that really take? Okay, there was a researcher who recently passed away named Bob Fuller at Nebraska-Lincoln, and he was a good friend. We had done several studies together over the years, and he talked about how to develop reasoning ability. That was one of the things that he focused on, and he had several graduate students that had done studies in changing reasonability. Most of those studies seem to show that it took a full year of study in a science class that was, one of these reasoning kinds of conceptual sciences to change reasoning ability. And so as I started looking at changes in the Lawson test, pre-post Lawson test course, okay, these are the sorts of things that I saw. So this is a GE Physical Science 100 class, and you can see that there's no change in Lawson test scores over the course of the semester. And the same thing here in a Physics 105 class. So this is algebra-based pre-med physics class. Okay, so this is a GE General Science, and this is I don't even remember what the numbers are here, but it's the algebra-based one. 111, I think, is what they used to call it. Anyway, now one of the things I want to point out here, this p-value, and I want to just head off some of whatever questions there might be about this, because the educational researchers don't generally use error bars. Okay, how you tell the difference between these two samples is with a p-value, and this represents the probability that these two groups could have come from the same sample and be as different in their means as they are. Okay, so what it really does is it measures the area in the tails of the overlaps. Okay, so with a high p-value, what that means is that there's no difference between them, between the two means. Low p-values, generally less than 0.05, or depending on what confidence that you want, sometimes 0.10, tells you that the samples really are different. Okay, so I'll point that out as we're moving along here, because you'll see this more. Okay, so now what I'm doing here in these classes, I have some clicker questions generally, so there's engaged, and some sort of homemade-like activities that some of them they'll do out of class, and sometimes they'll do in class. 105 doesn't now, but it used to have a lab that went with it. Now it's separate. But you could see that it's not making that big a difference in their reasoning ability. Okay?
Question?
Yes?
So is there a difference between scientific reasoning and reasoning in general? And if there is there also a relationship to what we might call IQ?
That there may be. I'm going to think on my instinct say that general reasoning ability is roughly equivalent to scientific reasoning ability. These sorts of games that we used to play about that there's 5 people and one of them has a beard and one of them has this color hair and one of them has this kind of car, who's who? You remember those kind of games? That's a perfect example of sort of reasoning ability that a scientist or somebody else is going to approach it the same way. Okay, so I think in general reasoning probably is a fair proxy for scientific reasoning. The other part of your question?
Well, is there a connection between...
Oh, between IQ, that's right. Possibly. I'd have to think about that. Yeah?
It seems like it would have a greater correlation to EQ than IQ.
Tell me about EQ.
Emotional.
Emotional, maybe.
Yeah, it's just something that's
Yep.
Actually, I think there is this Canadian psychologist by the name of Keith Stanovich who does this kind of research where IQ is related to the rational thinking, and he found almost no correlation. So you have these people
who are really smart but won't reason.
Yeah. Actually, calling the term disrationality. Why smart people do stupid things?
Okay. Yeah, I was talking to somebody about that the other day, where he said that there's all these brilliant people that have no horse sense. That's what he called it. Yeah, very good. Thank you. Any others? All right. So the point of this is that with even what I thought was a more innovative, sort of less traditional classroom, I'm not seeing changes in their reasoning ability over the course of a single semester. Okay. So what I did is I, several years ago, went to a seminar where Lillian McDermott came and talked about her tutorials in introductory physics. And I was hesitant to give up one of my days a week to these activities. But I said, okay, I'll try it. And this was the result. This was, let's see, these are both Physics 105 classes. And this one's a couple years ago, this one's like 4 years ago. So this one, the p-value is 0.001, this one's 0.017. So they're both statistically significant. Okay, so we're talking about a statistically significant change in reasonability over a single semester, not just over the course of a whole year. Just by adding these relatively self-contained activities in the classroom. But they are specifically research-based, where it leads them through step-by-step question to say, okay, what do you think about this? And then it says, all right, if that's what you think, then what will happen if you do this? And then it says, okay, if that's what you did, is that what happens? And it never is. Okay, that's the way they put them together. So then they say, okay, now go back and think about what you answered at first. Okay, so they specifically and explicitly exploit your reasoning. And what comes out of it, actually, there's two things. The first one is that the students, by the end of the semester, they'll say, I have learned that whatever I thought at the beginning of the tutorial is just assume that it was wrong. But that they really do figure it out, and that their learning is deeper and more robust. Okay? So, here are several examples. I tried when the Knight textbook, Larry Knight wrote a physics textbook, both for introductory physics and for scientists and engineers. And accompanying that textbook, he had a workbook that had tutorial-like activities and questions in it. And I thought, this will be less expensive than the tutorials, and maybe it will take less time. I can assign them to do it outside of class instead of taking class time for it. And what I saw was smaller gains in their reasoning ability, right? Although, you might say, okay, so their reasoning ability changed. Does that correspond to understanding the concepts better? Because that's what I really care about, right? I want to see if they understood physics better. And did they? So this is pre-tutorials. This is post-tutorials. Yes, it made a difference in the conceptual understanding.
Have there been like long-term studies done that trace a person over?
Not very many. Not very many. The logistics of what they call longitudinal studies are hard. There was a guy at Montana State who worked with Lillian McDermott's group as a graduate student. Actually, I think he may have been a postdoc. His name's Greg Francis. He did a study like this on students that he had access to over the course of their 4 years, and showed that with kids that had these more innovative, interactive tutorials, not tutorials, but these more interactive experiences in their classrooms, that their scores on the forced concept inventory 4 years later were still passing. Where kids that had had a more traditional kind of experience, when they took the forced concept inventory 4 years later, they were guessing.
Did the actual score decline at all?
Yes, for the, I think a little bit for the more interactive ones, but the kids that had not had the interactive classrooms, that their scores had gone back to where they were when they were guessing. So they declined significantly.
I assume you're talking about non-physics majors.
Both.
So you had physics majors who couldn't pass the forced concept test
after 4 years. Yeah, it's a little scary.
It's a lot scary.
Yep. And it's interesting. If you're gutsy enough to try it, let your graduate students take it.
So I went to the University of Minnesota for graduate school.
Okay, with Ken and Pat Howard.
Pat made us take it when we entered as graduate students before we were allowed to TA, because they wanted to put us in the shoes of those kids. And there were 2 people in my class who got a perfect score, but everybody else, the average was not as high as you would expect it to be.
Yeah. Yeah, it's interesting how persistent some of these, particularly in force issues, are.
Yeah.
But you know, the studies over the last several years have also extended these things into upper level classes. I went to a talk at the APS meeting in Denver several years ago where, and it wasn't really, but the guy gave a talk called Jackson by Inquiry. Yes. Yeah, and I would love to have taken that class because I still don't remember Jackson.
That's
But
because your experience wasn't painful enough.
yeah, that's, I was sufficiently afraid. Anyway, so it matters. It helps. Okay? So in conclusion, an hour later, okay, if what we really care about is that we learn this stuff, that they learn this stuff, that the people, not just that are going to be our colleagues, you know, that we're going to work with in 10 years, or the people who are going to be sitting on our NSF grant proposals, or who are going to be making decisions about, you know, healthcare or whatever is your cause du jour, it's helpful for us to be responsible about teaching in a way that works, that is consistent with what we understand about how people learn. Okay? So what really matters is interactivity. They got to be engaged, minds on and hands on. Okay, as much as we can. So be explicit about paying attention to reasoning ability. Point out when something is happening that is demanding them to reason. Pay more than just lip service to, let's think about this, think our way through this. Okay? And thank you to be able to be back here in this setting and to resurface all of these memories, and Dr. Tatar and Dr. Williams that I've respected for these many years. Thank you.